Hello, everyone. Welcome to the UH Energy Electric Vehicle webinar series. And today we will have the pleasure of discussing next generation batteries for electric vehicles and stationary storage. My name is Andres Bryan, and I'm a biomedical engineering student at the University of Houston, and I will be the moderator for today's event. So before we begin with the event for today, I want to take a minute to thank our partner Evolve Houston, as we are very fortunate to have them working with us to help provide Houstonians with reliable alternatives for transportation. I'd also like to take a moment to remind everyone of our next webinar on January 20th, where Dr. Rajasekara will address current trends and future strategies in electric and hybrid vehicles. To learn more about the electric vehicle webinar series and Dr. Yao's research, please visit the UH Energy webpage using the link above. So moving forward, we will have the Q&A session at the end of the presentation, so please hold on to your questions until the end. That being said, we will be utilizing the chat function, so if you have a question, go ahead and send it in, but we will answer the questions at the end of the presentation in the order they were received. So without further ado, I would like to introduce Dr. Yan Yao. Dr. Yao is currently a professor in the Department of Electrical and Computer Engineering at the Cullen College of Engineering in the University of Houston. He received his BS and MS from Fudan University in 2000 and 2003, and PhD from UCLA in 2008. All of these degrees were received in materials sciences and engineering. Dr. Yao is recognized as a leading expert in materials for energy conversion and storage, with his recent research interests including solid-state batteries, multivalent ion batteries, and aqueous batteries. Dr. Yao is the author of 110 peer-reviewed articles and 10 US patents, as well as a recipient of many prestigious awards. So the quest for cheaper, safer, higher density, and more resource-abundant energy storage has driven significant battery innovations. In the context of material development for next-generation batteries, organic battery electrode materials that store charge with dedicated redox groups have emerged as an exciting option, complementary to inorganic materials, and demonstrated unique advantages in novel battery technologies. Therefore, in this presentation, Dr. Yan Yao will review his group's research activities in energy storage, including a number of case studies. Dr. Yao will emphasize this organic battery materials design in emerging rechargeable battery technologies, such as solid-state batteries, multivalent metal batteries, and aqueous batteries. Dr. Yao will also discuss an integrated battery diagnostic platform for structural, chemical, and mechanical characterizations that could provide fundamental insights into the failure mechanisms of solid-state batteries.
Hello, everyone. Thank you for coming to this webinar. My name is Yan Yao. I'm a professor of Electrical and Computer Engineering Department at the University of Houston. I'm also a PI of Texas Center for Superconductivity. I also appreciate Professor Ramana and Andres for the invitation. So recently, lithium-ion batteries and electric cars have been a huge hit in the news. You may also heard about Tesla's stock price skyrocket 7 times since beginning of this year, and the current market value over $600 billion. You may have also heard about a solid-state battery startup called QuantumScape went public last month and showcased their hit and home run technology earlier this week. So in today's webinar, let me remove the heat of the batteries, lay out the battery challenges we face today for both electric vehicle and the stationary storage application. I will also show you the research we have done in my group to address these challenges. So to predict the batteries for the future, we need to look back at the history of batteries. So batteries have over 220 years history since Volta invented the voltaic pile in 1799, who discovered electricity could come from chemical reactions. So this led to the birth of electric chemistry. So in 18th century, fuel cells, lead acid batteries, nickel cadmium batteries have been invented. All this battery using water as the electrolyte, and they show high rate, but the voltage is limited up to 2 volts. In the middle of 19th century, beta alumina as a ceramic has been discovered for sodium-ion conductors. The Ford motor pioneered high temperature sodium sulfur batteries. So this is the first device using solid state electrolyte. Interestingly, what we hear most often is the lithium-ion batteries, a relatively young field. Research started in early 1970s on lithium metal. Then integration cathodes were developed. Commercialization of lithium-ion batteries started in 1991. So in contrast to aqueous batteries, lithium-ion batteries using non-aqueous electrolyte that enable forward batteries. So looking at this last 220 years, if you ask what is driving the battery technology development, the answer is the energy density. Energy density states how much energy you can store in total weight or in total volume. So this kind of battery have 5 times higher energy density compared to that of lead acid batteries or nickel metal hydride batteries. Battery is a complex interdisciplinary research field, not only involving electrochemistry, knowledge on semiconductor, solid-state physics and chemistry, solid-state ionics are also important. So there are many scientists shown here contribute to the fundamental concept of battery research. Those highlighted in red received Nobel Prize related to batteries research. So excitingly, last year, a Nobel Prize in chemistry goes to 3 gentlemen for the development of lithium-ion batteries. Jiang Goodenough demonstrated the first 4-volt cathode using lithium cobalt oxide. Later, lithium magnesium oxide and lithium phosphate were also discovered by him. So Jiang received the award at the age of 97. Stan Whittingham discovered the integration concept for rechargeable batteries in 1970s. Akira Yoshino developed the first prototype of lithium-ion batteries in 1985. So then a commercialization of lithium-ion batteries was developed by Sony and Asahi Kasei in 1991. So since the last 3 decades, we have witnessed the astonishing growth of lithium-ion batteries that have fundamentally changed our lives. Last year, the lithium-ion battery annual production reaches 300 gigawatt hour and is projected to surge to 2 terawatt hour scale in 2028, just based on electric vehicle market alone. So to get that number, a battery breakthrough is needed. So you may know currently every year there's 100 million cars are sold every year. However, there's only 2% are electrified today. The reason for that 98% cars are not electrified are because today's batteries are not competitive with the internal combustion engine. More specifically, today's batteries does not have extremely high energy density, which limits the driving range. You also do not have the ability to charge a battery as quickly as you can refuel the gasoline engine vehicle. So in many cases, the batteries are expensive, therefore driving the cost above mainstream vehicles. In many cases, batteries doesn't last long as the vehicle itself. So finally, the batteries are made of liquid electrolyte. These batteries are using liquids which are hydrocarbons, which means they are fuels and raise safety concerns. So I believe the batteries that can address all these 5 limitations can narrow the gap with the combustion engine and dramatically increase the penetration to 98% of non-electric market. So that's why Bloomberg New Energy Finance predict electric vehicle batteries would increase from 2 to over 50% in the next 20 years. So in addition to electrified transportation, transition from traditional centralized electric grid to decentralized smart grid, where clean energy and the Internet of Things play a significant role, is another big trend. So traditional grid are demand-driven, have almost no storage capabilities. Storage of electricity by batteries could reduce the consequence of severe weather condition, improve the response of the grid, and make it less complicated. Station battery can make profit when the electric cost is low to charge the battery and sell the electricity to the grid when the price is high. So this requires the cost of battery to be less than 5 cents per kilowatt hour per cycle. However, today's batteries are too expensive to reach this target. So in many cases, the battery do not last 5,000 cycles. In today's batteries for the grid are also not safe enough. So imagine a deficit situation could happen when a megawatt hour scale battery catch fire. So it's clearly a battery for the electric grid should be designed differently from electric vehicle batteries because the cost, cycle life, and the safety are higher priorities than energy density in this situation. So my group has been working on both lithium-ion and lithium metal batteries for high energy applications. We have developed a diagnostic platform for understanding cell failure mechanisms. We have also worked on developing new manufacturing process to reduce cost. For grid-scale storage, we work on multiple beyond lithium-ion battery chemistries. We focus on intrinsic safe and low-cost battery materials by choosing earth-abundant organic materials. We can also choose earth-abundant sodium and magnesium metals as anode. So in the rest of my talk, I will show you 3 examples. The first is a high-energy solid-state lithium battery. The second is a diagnostic platform. And finally, high-power magnesium batteries for the grid application. Let me start with the high-energy solid-state organic lithium batteries. What is solid-state lithium metal batteries? So I borrowed a slide from QuantumScape, a startup working on this field. So on the left is conventional lithium-ion batteries. You have a cathode and anode separated by a porous polymer separator. So the entire cell is flooded with a liquid electrolyte, which is a medium for lithium-ion to travel. In a solid-state lithium metal batteries, you can use the same cathode, but replace the porous polymer separator with a ceramic separator. You could use lithium metal as anode, or in the anode-free design, lithium metal could be plated during the initial charge process. Due to the reduced volume and the mass compared to that of lithium-ion batteries, lithium metal battery can potentially double the energy density from 250 to 500 watt-hour per kilogram. So this could enable a greater driving range, 15-minute fast charge, and a safer operation due to non-flammable electrolytes involved. However, there have been extremely difficult to do so, particularly plating and stripping lithium metal at such a high rate without any side reaction has been extremely challenging. I hope to see more details how QuantumScape was able to accomplish this in the future. The leading cathode material using all solid-state batteries are mainly nickel, manganese, cobalt oxide, short for NMC. So even solid-state batteries can work well. The cost of battery would still be high due to the nickel and cobalt used in these cathodes. So to make cobalt-free and nickel-free cathodes and reduce the cost, we propose to using organic electrode materials, which are made of carbon, hydrogen, oxygen, without any transition metals. So organic compounds with well-understood redox active function groups can reversibly store and release multiple electrons and cartons per molecule. So organic lithium batteries has the potential to deliver material level specific energy over 1,000 watt-hour per kg, place them in the same category as NMC lithium and lithium sulfide batteries. So Fang Hao was the first graduate student who worked on this project. He's now at the GM R&D Center. The organic we used in this research is called PTO, and each molecule undergoes 4 electron reduction along with 4 lithium ion insertion into the molecular crystals and coordinating with oxygen atoms. So the reaction corresponding to a theoretical capacity of 409 milliamp hour per gram. So the cathode composite was prepared by mixing PTO LPS electrolyte, and carbon with a pestle mortar mixing, followed by uniaxial powder compaction. So the PTO lithium cell exhibits a discharge voltage about 2.2 volt with a specific capacity about 320 milliamp hour per gram, corresponding to a material utilization of 78%. So the cell cycles stably at the 0.3 C for the initial 200 cycles and maintains 61% of its maximum capacity over 1,000 cycles. So this is a truly remarkable capacity and stability for new cathode materials in solid-state batteries, which have been studied only recently. To understand the stability, the evolution of the cathode electrolyte interface was probed by in-situ electrochemical impedance. The Warburg coefficient can be extracted from the electrochemical impedance spectra, which reflects ion diffusion resistance as a cathode electrolyte interface. What we see here is that the AW remains low during the majority cycle, but increases sharply when the voltage exceeds 2.9 volts versus the lithium, at which the potential oxidation of electrolyte is expected. So upon discharge, the AW quickly reverts to lower value and remains so until the charge to the high potential in the next cycle. So we note when NMC is used in solid-state cells, a thin oxide layer coating is necessary. Otherwise, we will see irreversible increase of individual resistance. So the fact that no coating layer is required for PTO is due to the moderate working potential, and thus which enables a longer cycle life for this battery design. To further improve materials utilization, we look into optimizing the microstructure of the electrode. So in contrast to NMC particles, which have uniform shape and size, organic typically have wide distribution of the shape and the size, making it very difficult to engineer the microstructure. So we discovered a cryo-milled process can greatly reduce the PTO domain size. From the cross-section SEM images, the black phase is a PTO with carbon, and the white phase are solid electrolyte phase. So we have therefore segmented the SEM images based on grayscale. We see the size of PTO domains for cryo-milled samples is about a factor of 10 smaller than hand-milled ones. Such significant reduction in the size of the active material contribute to the improved battery performance. Now the cryo-milled sample reached the capacity of over 400 milliamp hour per gram, which is a material utilization of over 99.5%. So this is the first time organic electrolyte material accomplished full utilization in a ceramic electrolyte-based battery. So the material level specific energy also reached 828 watt-hour per kg. This is only the material level, not the full cell level. But nevertheless, this puts the organic, the best solid state chemistries and shows the potential for organic electrolyte materials in enabling high energy batteries. The cycling performance of the cryo-milled sample is also very good. At 0.3 C, maintains 100% of its maximum capacity after 100 cycles. However, one remaining key issue is the low mass fraction of PTO in the cathode, only about 20%. So Dr. Jibo Zhang took the challenge to increase PTO mass fraction. Jibo found while increasing the PTO fraction from 20 to 50%, specific capacity decreased quickly. This corresponding to utilization from 80% to 32%. So in other words, the capacity didn't scale with PTO ratio following this theoretical line, but reach a plateau and do not further increase. Jibo found the origin of this low utilization is due to the unfavorable microstructure. Electrolyte islands with size between 2 to 15 micrometer were surrounded by a sea of PTO and carbon mixture. Such a microstructure is unfavorable for lithium ion transport because electrolyte couldn't find the percolation network, and the PTO has a lower ionic connectivity for lithium-ion transport. So the reason for forming such undesired microstructure is related to the soft and compliant nature of organics. Organic deform easier before lithium-ion solid electrolyte deforms. So to reverse this microstructure, we actually invented a solution process method that preforms the core shell structure particles, where the PTO core is surrounded by the electrolyte shell. So the deformation of PTO during the uniaxial pressing process could change the microstructure compared to the dry process. The cross-section of solution process composite at 40% active material shows that phase separation is clearly reversed. Now the electrolyte domain forms a continuous network with the PTO domain embedded in between. This is in contrast with the dry process, the same PTO fraction. So although this is solution process, we have to dry the solvent off in the oven to make it fully solid state. We also did the top seams measurement. The images not only confirm that's more uniform spatial dissolution of PTO in the solution process compared to those in the dry process, also provide molecular information of the interface. So we find the green one related to the PTO is partially reduced to form lithium X PTO, and also electrolyte is partially oxidized to polyphosphate. So solution process also result in slight increase in ionic connectivity and a 6 times increase in electronic connectivity, so leading to a balanced transport in the solution process sample. We note here, typically reactions between cathode and electrolyte is to be avoided or suppressed. For example, coating on MC particle oxide coating is used. However, here is an example showing the reaction between cathode and electrolyte can be used for the benefit of forming a better microstructure. So as a result, the area capacity now scales with PTO mass fraction in this red line. In comparison, the dry process is a blue line. So the materialization actually can go up to 98%, and cycling stability is excellent over 100 cycles. We also compare the specific energy considering the total cathode mass in this figure. So the value can reach 300 watt-hour per kg, which is on par with inorganic cathode, such as the lithium cobalt oxide, which has a lower capacity but a higher voltage. But we show better cycling is possible without any coating applied. So this work shows our effort in using earth-abundant materials that potentially can lower the cost and reduce the reliance on any metals. There are also still many challenges to overcome, such as low density of organics, or reduce the electrolyte thickness to less than 50 micrometer to improve the volumetric energy density and rate performance. So that's the first example. So in addition to the new material discovery for solid-state batteries, our group is also working on a diagnostic platform for better understanding of cell failures and mechanisms. So UH and RISE form a collaborative team to approach the complex origin of battery failures. This work is funded by DOE VTO office. So the failure mechanism of a solid-state lithium battery may be briefly attributed to two main causes. One is the interfacial resistance increase, and second is about lithium dendrite growth. So the resistance increase may be attributed to electrolyte decomposition at the interface void formation, so which happens at both cathode electrolyte and anode electrolyte interfaces. So we decide to approach this complex origin of battery failure using not only one technique, but a combination of 3 techniques as a tool set, including the time of flight SIMS measurement for chemical analysis. We will use FIB 3D reconstruction inside the SEM for structural analysis. We are also using in-SEM nano-indentation for mechanical analysis. The operando characterization requires transferring the cell between the instruments without exposing to the air. So therefore, we first developed an air-free transfer vessel. At the heart of the vessel sits a cell test platform, which is equipped with a microcell mount, where electrochemical tests can be performed in situ. Heating and pressure sensing module are also integrated in this platform. This slide shows an example of SEM observation of a cross-section of the thin cell mounted on the platform. The SEM shows a cross-section of tri-layer structure of cathode, NMC, and the lithium electrolyte, and this electron layer and this lithium layers. So we can also perform the Raman spectroscopy on the same thin cell and the same area. So that test platform has been also optimized to deliver performance similar to non-micro cells. The first discharge capacity reached 200 milliamp per gram, which is comparable to that thin cells. So the pressure change can also be monitored in situ. So this results indicating the efficacy of the vessel in isolating the test platform from ambient condition without interfere any analytical beams. So for mechanical characterization, a similar transfer vessel containing a nano-indentator has also been developed. So this image showing the vessel inside the SEM opens the cover, can expose the tool we used for mechanical measurement. So this is a Histron nano-indentator. So special result mechanical test can be performed by locating the diamond tip at different locations. So when this shows that when the tip is located for lithium cobalt oxide particle, we can extract the modules and hardness for the lithium cobalt oxide. So if the tip intends electrolyte area, we will also see the measurement of the modules of electrolytes 1 magnitude smaller. So in situ, SEM nano-indentation has high spatial resolution to probe the heterogeneous composite cathode, in this case, to separate, differentiate the cathode versus electrolyte, and even to measure the mechanics of the interface. So finally, we also equipped with a focused ion beam SEM using slice and view function. They can enable a reconstruction of the cathode composite. In this example is a PTO LPS freeze mill sample. We can resolve the network of electrolyte. This is the PTO cathode, and we can also see the pores connectivity structure in the cathode composite. So segmentation of the 3D images provide information such as volume fraction and the tortuosity. And also we can see the pores in this cathode composite is less than 1%. So in summary, this work is to develop a platform for structure, chemical, and mechanical characterization in solid-state lithium batteries. The in-depth understanding allows us to effectively predict and optimize the physical and chemical properties during the charging and discharge process. Now we have discussed lithium metal batteries. Let's switch the topic to magnesium metal batteries for grid-scale energy storage. So there's a need for grid-scale energy storage becomes more and more pressing. We have sought to less expensive and more readily available element alternative to lithium metal. So magnesium is among the top 10 most abundant elements in the Earth's crust. Compared to lithium, here at least 2 orders of magnitude higher than that of lithium. So in our recent review published in Nature Energy, we reviewed the current status of the multivalent metals, ion battery research, and provided a roadmap for future development. So among many metals such as magnesium, calcium, zinc, and aluminum, magnesium battery is considered one of the prime candidates. The direct use of magnesium metals as anode is important. Magnesium metal has a reputation of dendrite-free plating as complex crystals. So this is in sharp contrast with lithium metal growth behaviors. However, recent years, reports have shown magnesium also forms dendrite when the electrolyte is not fully optimized to have highest cooling efficiency. So a major challenges for magnesium battery is the lack of efficient cathode material. So magnesium ions have twice the charge of lithium, while they have similar ionic radius. So magnesium cations are more polarizing than lithium. So as a result, magnesium dissolution from electrolyte solvent or dissolution with its ions need to overcome a huge energy barrier like this. Furthermore, after this dissolution or dissociation, the integration into the cathode also needs to overcome a high energy barrier because of strong primitive interactions. So there are two approaches to address these challenges. The one is the cycle the battery at the elevated temperature. For example, 60 degrees C, Doran Alvarez group have shown that shower phase can reach theoretical capacity. So the other approach is to storing magnesium ions in its complex form, such as using DME molecule solid magnesium ions. So both approaches have disadvantages because elevated temperature would require a heater, which is not very practical. Storing complex ions would lead to a limited cycle life caused by volume change due to cold insertion of the bulky solvent molecules. So therefore, the cathode materials require new reaction mechanism to support a fast magnesium 2+ storage. In our recent work, we have demonstrated heterogeneous enolization redox cathode chemistry to circumvent the ionic dissolution and solid-state diffusion challenges. PTO was again selected as a model compound due to its high theoretical capacity and solvent-free magnesium storage. So the voltage profile consists of two plateaus, each corresponding to 2 electron reactions. The average discharge voltage is about 2 volt, and the capacity is about 315 milliamp hour per gram. Both of these values represent one of the highest value for magnesium batteries. So we probed the cathode reaction mechanism using UV visible spectroscopy. The reduction of PTO in the magnesium electrolyte actually is a heterogeneous liquid-solid reaction. We use a switch-lock cell and we discharge to different DOD and then dilute the reaction electrolyte with DME. What we see is that the PTO is reduced to soluble magnesium 1 PTO intermediate and then to insoluble Mg2 PTO. So the precipitation of Mg2 PTO is a spontaneous process that overcomes the solvent stripping from magnesium. Look at the chemical reaction. PTO reduction involves no covalent bond breaking process. So that's why the reaction is intrinsically very fast because there's no bond cleavage or reformation in the cathode. Here we show that PTO electrode at the very C rate. At the 5C, the power is 3 kilowatt per kilogram, surpassing the state-of-the-art magnesium batteries. So this is a new class of redox chemistry which bypasses the need of solid-state diffusion while solely storing magnesium instead of its complex ion kind of forms. Like other liquid-solid reaction-based batteries, soluble reaction intermediates bring two major concerns. First is a cathode mass loss caused by continuous dissolution. And second is that dissolved species will diffuse to the anode side and cause passivation of the metal anode. So both of these issues were controlled effectively in our system. The first solubility of magnesium 1 PTO actually is less than 1 millimolar. So this 100 times less than that of polysulfide. Dissolution of PTO is suppressed by inserting 2 micrometer thin lightweight graphene oxide membrane between the cathode and the separator to trap the magnesium 1 PTO intermediate, but still maintain electric contact because this graphene oxide membrane is electronic conductive. So all the capacity trapped by the Mg1 PTO can still contribute the capacity of the cathode. So this concept is borrowed from lithium sulfur battery and has been proved very effective. The battery has an initial activation step due to the high viscosity of G4 electrolyte. Then it becomes stable for 500 cycles with a capacity retention over 84%. So on the second question about magnesium surface passivation, we test magnesium plating in G4 solution with and without magnesium 1 PTO. We see there's no variation in overall potential in the plating and the streaming process, indicating there's also minimum change on the metal in the PTO cell. However, in comparison, when magnesium sulfur reaction, the intermediate, we can see the overpotential has almost been doubled. So this probably is related to much higher solubility of the intermediate reaction in Mg sulfur reaction process. While the fast kinetics has been shown earlier, the cell power is still limited by the mass transport in the MMC G4 electrolyte. So Rana and Oscar from Toyota tried a variety of solvent blend and found several mixture solvent provide much better solubility. Here we use DME and G2 as a mixture, which provides a best solubility, reaching ionic conductivity of 6-fold increase. So we have observed a mixed solvent shell of magnesium from NMR studies here. So cyclophotometry shows a 99.9% Coulombic efficiency, reaching impressive 100 milliamp per centimeter square. So this is 10 times higher than that of MMC G4 electrolyte. In asymmetric magnesium copper cells, even at the 50 milliamp per centimeter square, we still can reach a Coulombic efficiency about 99.7%. The morphology of magnesium plated on copper shows dense, smooth, and dandruff-free morphology. This is deposited at 20 milliamp per centimeter square for area capacity of 3 milliamp hour per centimeter square. So the smooth, we can also apply similar condition for symmetry cells over 5,000 minutes. The smooth voltage profile indicating effective mass transport in the electrolyte. So this results consolidate magnesium metal as a safe anode even under demanding conditions. So finally, we couple PTO cathode and new DME G2 electrolyte yield a high power magnesium battery prototype. We have shown at 20C and 50C, the capacity remain 200 and 210 can be retained. So stable cycling at the 5C can be maintained over 200 cycles. So the Regoni plot of state-of-the-art magnesium batteries store magnesium 2+ cations are summarized here. So intercalation cathode material such as Chevron phase or spinel TS2 shows low power even at 60 degrees C. The conversion cathode such as sulfur and iodine display a slow kinetics up to 2C. So in this work, our cathode relying on enolization redox mechanism shows a power of 30 kilowatt per kilogram. So 2 order of magnitude higher than the current highest. So in summary, this work developed a high power magnesium battery featuring organic quinone electrode and with a tailored boron cluster electrolyte. Future work needed to increase the PTO fraction and also lean electrolyte design. So, but this work sets a new direction for developing high-performance magnesium batteries. So in this talk, I have reviewed the challenges of batteries for electric vehicles and grid-scale batteries. Energy density and fast charging are the key to the EV batteries, while cost and safety are more important considerations for grid-scale batteries. We have discussed 3 examples from my group, from lithium also to magnesium. So I didn't have time to touch upon aqueous batteries in my group and also sodium-ion batteries. So central theme of this work is to use low-cost organic materials as well as the intrinsic safe electrolyte. So let me end my talk by acknowledging the people who actually did the work, the wonderful students and postdocs in my group. Some of them have already become professors somewhere in the world. I was very fortunate to work with those talented students and postdocs. So I would also like to thank collaborators and funding agencies here. So with that, thank you for your attention. I would be happy to answer any questions.
All right, thank you, Dr. Yao, for that informative presentation. We will now open up the floor to any questions the audience may have. And to do this, again, just go ahead and click the chat function. You can either direct message me or just send it into the main chat. But right now we have 2 questions. So the first one is, doesn't the solid state battery significantly improve function through preventing of defective structures?
Thank you for this great question. So exactly, one of the key advantages of the solid state batteries is that it can greatly improve the safety, because it replaces the porous polymer separator with a more ceramic layer of separator, which is a solid. Now, of course, you have to address the solid-solid contact. Typically, it's not very efficient. But this can also enable to use of the lithium metal, as I mentioned earlier in the first story, that with much thinner lithium metal, you dramatically can almost double the energy density from currently typical lithium battery is about 250 watt-hour per kg at the cell level to almost 500 watt-hour per kg. So in fact, I'm part of the so-called Battery 500 consortium that's set up by Department of Energy. 2 Nobel laureate, John Goodenough and Stan Whittingham, are part of this consortium. We meet every quarter and to discuss how can we enable lithium metal to work. So that's still that hold a lot of promise for next generation batteries, and also could potentially enable the battery to be fast charging technologies. Really enable the penetration of EVs to the market. So I'm not sure that's the question that's answered.
I think you did a good job. The second question was about the magnesium batteries, and is there a supply chain issue that is of concern that's similar to lithium?
You are talking about supply chain issue for what? For lithium? For what battery?
For the magnesium batteries, but is it would it be similar to lithium?
Well, that's a great question. Actually, magnesium battery has not been commercialized. People has worked on this in the last 20 years. The progress is relatively slow. Our work published last week, actually in Nature Energy, I think is one of big breakthrough in this field. Basically we can enable high power magnesium, but still this is a proof of concept stage. So I would say the technical readiness level is around level 3. So still a lot of work need to be done to really move this to a real prototype or even a product. So at this point, even the the supply chain does not exist. The main reason is that electrolyte and the cathode is not finalized for this battery chemistry. Remember, this is a relatively new lithium-ion batteries actually started in 1970s, right? It commercialized after 20 years of hard research from hundreds of scientists and engineers. It took about 20 years for lithium-ion batteries to become commercialized in 1991 by Sony. And magnesium, I think, is also going to take a longer, take some time to become, if it can be commercialized. But definitely we can borrow what we learned from lithium-ion batteries, and it definitely show the advantage compared to lithium-ion. So at this point, it's still very early stage technology.
All right, thank you. And another question that we have is there a significant cost increase associated with solid state batteries, or does the removal of cobalt and nickel offset the increase in cost for density?
Well, that's another great question. Again, solid state lithium metal battery, it's a hot topic, right? So many companies are working on this. People think that's not next generation battery, but however, there's no product. Again, it's this at the verge of this being commercialized. The company I mentioned called QuantumScape went public through SPAC, right? So basically, they treated recently. I think they went with a company from Canadian. So somehow they work together with Volkswagen. They spent, I think, $300 million in last 10 years to reach today. It's a performance, which is at a single year, rather small cell. So I think they would not have their product until in next 3 or 4 years. So in terms of cost, at this time, the cost is very high. Right? It's much higher due to the process has not been, the manufacturing is even harder. So they have demonstrated the prototype can work, relatively small size, but there's a lot of work to do to really develop the manufacturing. And Elon Musk said, typical prototype is 1% of effort, and manufacturing is 99% effort. So it's still a lot of hard work to do. But regarding the cost, NMC, because nickel and cobalt involved, although cobalt is only 10%, nickel is 80%, still remain a major cost a fraction of the cost of the batteries, even in solid state lithium metal batteries. And so people are developing alternative, cobalt-free or nickel-free oxide, like lithium phosphate. That's one option. So my work from our group is trying to develop completely organic-based. So only has carbon, hydrogen, oxygen, sulfur, nitrogen, which you can produce either by a renewable like biomaterials or from the oil gas industry. So there's no element abundance limitation, right? So we are only a few groups in the world are doing that. We show that's great promise in achieve. There's only probably one of 3 possible cathode material can be used in solid state batteries. So we are actually working with a company trying to solid state battery company, which is I think also top in the United States, to explore the possibility how much cost reduction it can result. So we are pretty positive. This could be another important breakthrough in terms of cost for solid state batteries.
All right, thank you. Does anyone have any questions that they would like to ask? All right. So if not, we are going to go ahead and draw this webinar to an end. But before we conclude, I would like to say that all of the full video will actually be online on the link that we mentioned earlier. So I would like to say a big thank you to Dr. Yao for having such a wonderful presentation, our partner Evolve Houston, and everyone in the audience for attending this event. Without all of y'all, we would not be able to have these possible. So please join us for the next electric vehicle webinar on January 20th, 2020, where we will be discussing with Dr. Rajashekara electric and hybrid vehicles and their current trends and future strategies. So thank you again and have a really good day.